In this video, we'll look at how to perform low-impedance two-port shunt-through impedance measurements to measure non-idealities of real-world components such as inductors and capacitors. In future videos, we'll use this technique to measure the actual power distribution network impedance profiles on PCBs. Here we'll go through measurement basics, calibration, what to watch out for when you're performing these measurements, and finally we'll measure two components, an inductor and a capacitor, to extract their parasitic elements such as equivalent series resistance and equivalent series inductance, and see how our measurements compare to the manufacturer provided data. If you haven't already, make sure to check out the previous video on capacitor measurement and modeling, which shows other impedance measurement techniques, for instance using an impedance adapter. A huge thank you to JLCPCB for sponsoring this video. The PCBs we're using in this video and in future videos were manufactured and assembled by JLCPCB, and they did an absolutely fantastic job. JLCPCB provides easy, affordable and reliable PCB and PCBA services. The web interface is super easy to use, as well as their PCB and PCBA prices are absolutely incredible. A 10 by 10 centimeter 6-layer PCB VN pad with Enix surface finish is only $35 for 5 pieces, and their assembly is similarly affordable as well. I've also found JLCPCB to be super reliable with a high quality, and I can get my PCBs back in about 1 or 2 weeks, which is absolutely incredible and allows me to work at a much faster and better rate. Make sure also at the time of making this video, you can get $30 off with a coupon for JLCPCB's 6-layer PCB services. Links will be in the description box below as usual. A huge thank you also to Altium for sponsoring this video. If you'd like to give the powerful Altium 365 platform a try, make sure to follow the link in the description box below or go to altium365.com/yt/philslab and you can get yourself an Altium 365 free trial. Altium 365 brings many impressive features to Altium Designer: collaborative design reviews, mechanical co-design with SolidWorks, Fusion and more, manufacturing collaboration, ease of BOM management, and much, much more. If you'd like to check out in part some of the cool features of Altium 365, you can also go to my GitHub profile and my GitHub IO page, pms67.github.io, and check out some of the example hardware designs that were shown on the YouTube channel here. With the Altium 365 viewer, you can explore the boards in your own time and in real time. You can look at the 3D models and you can scan through the PCB layers as well as the schematics on some of the designs as well. I'll leave links in the description box as usual. To start off with, let's go through the basics of the two-port shunt-through impedance measurement technique. The technique itself actually is quite straightforward. We typically will use a network analyzer or vector network analyzer with a single output port and a single input port. From the output port, which connects internally to a signal generator with known output impedance, we connect a coaxial cable to our device under test, or DUT for short, in this shunt or parallel configuration, and from that same connection point, we feed a coaxial cable into the input of our vector network analyzer with a known load or input impedance. This is simplified on the top right-hand side in this schematic block diagram. We have a signal generator, which we can control with a known output impedance, typically 50 ohms. We hook that up to this shunt DUT in parallel with our input impedance of our port 2. And this looks very much like a potential divider, or something we can figure out what the device under test impedance is, as we know all of the other parameters, at least in the simplified drawing. This two-port shunt-through measurement is a great impedance measurement technique for low impedances, meaning with care we can get down to the micro-ohm impedance measurement range. However, this technique isn't particularly great at measuring very large impedances, so we have a certain impedance range or impedance band that we can measure quite accurately. As we see here, this emulates a 4-wire Kelvin connection, and in fact this two-port shunt-through measurement is an S21, so an S-parameter transmission measurement that is translated back to impedance using the formula below. But typically we don't have to worry about this formula. Impedance measurement tools will do that for us in most cases. Now, measuring low impedances is all well and good, but why is this actually useful? Here are some examples. For one, we can measure components, for example capacitors and inductors, and look at their parasitic elements, such as the equivalent series resistance, equivalent series inductance, self-resonant frequencies, leakage inductances, capacitance, and so on, which we can then use to model the non-idealities and then use them in simulations, be that in SPICE simulations or EM simulations. Make sure to check out my previous video, which goes more in depth on capacitor measurement and modeling using a different impedance measurement technique. Links will be in the description box below. More importantly, and what I'm most looking forward to creating videos on, is that of power distribution network or PDN measurement. So measuring impedance profiles of the power distribution networks on real-life printed circuit boards. Seeing what we can do to keep our impedance flat, to keep our overall PDN impedance below a certain target impedance. We can look at regulator stability, and this will all happen in upcoming videos. So this is pretty much a prerequisite video for those future videos. Again, in this video, we will be looking at the measurement basics, setup, what to watch out for, as well as how to perform a calibration. And then we'll perform 2 example component measurements, one of an inductor and one of a capacitor. My particular tool of choice is the Omicron Lab Bode 100, which is the industry standard for low frequency vector network analysis. It has a frequency range of 1 Hz to 50 MHz. We have a large dynamic range, impedance ranges down to 1 milliohm and even below. This can be useful for component measurements, impedance measurements generally, measuring power supply parameters such as stability, input-output impedance, and more. I'll leave links to this in the description box below, but some of my favorite videos on these measurement techniques are by Picotest and Omicron Labs, and they do have a YouTube channel and very well done app notes. There are, of course, other tools to perform these 2-port shunt-through measurements. You could use a normal vector network analyzer or even a cheap one such as a Nano VNA, but keep in mind you will have different dynamic range limitations and different frequency range limitations. With any measurement technique, it will have its own limitations. In the previous video on capacitor measurement and modeling, we used an impedance adapter which had its own limited impedance and frequency range, which is in this blue shaded area on this graph. For our shunt-through measurement technique, which we can see on the bottom of this graph, we can seemingly measure down to very low impedances, lower than that of the impedance adapter. So that's always something we have to take care of and keep in mind that we have limits on the lower bounds and upper bounds of our impedance measurement ranges, as well as the frequency ranges. In addition to that, there are some other things to watch out for that I'd like to call out here. Again, the impedance range is limited, something around the milliohm, sometimes even high microohm range to hundreds or kiloohms for this particular 2-port shunt-through measurement. Now, there are things we can do, for example, add a low noise preamplifier to increase the sensitivity, which might allow us to measure lower impedances. We can also add a series resistance or series resistances between the shunt element that adjusts the impedance range and can also help to protect our measurement device in case you want to apply higher voltages or higher signals. The frequency range is also limited, in this particular case of the Bode 100, to less than 50 MHz, which is pretty much sufficient for most power design applications, but if you're characterizing RF components, of course, this might not be sufficient. What is very important that we need to do is calibrate our system to remove the effects of cables, our measurement setup, and more. That is the connectors, the cables. If we're using any bias injectors or DC blocks, they also need to be calibrated out, so we're just focusing on the device under test. We'll see we'll have 2 different calibration techniques, that's open short load or a through measurement. Another thing is we can't directly apply a high DC bias to the measurement. The max output voltage of the Bode 100 is limited to 3.3 volts RMS, and the max input voltage at port 2 with a 50 ohm input impedance is limited to about 7 volts RMS. So if we're trying to characterize the DC bias effects of inductors and capacitors, we'll need to use something like a DC block and a bias injector, one I had designed and fabricated by JLCPCB, you can see in the bottom right hand side. This will be a topic for a future video. Secondly, the 2-port shunt method also has a drawback, at least in the case of certain instruments, is that for the Bode 100, we have the output port and we have the input port, which in our case will be channel 2. Their grounds are not isolated. They're actually tied together internally. Plus, we have these 2 coaxial connections to the device under test, which means we do have a ground loop or low frequency ground loop. And this can cause errors in the measurement, and it can cause difficulties in measuring impedances below roughly 20 milliohms in frequency ranges of 10 and 100 kilohertz and below due to this ground loop. Now, there are some solutions to this. One is to use a common mode choke, so one by Omicron Lab, which we'll be using in this video, is pictured at the bottom, or we could use a differential amplifier, and we can improve the low frequency performance by, for instance, using low shield resistance cables, connectors with low ground contact resistance, and so on. So if you want to measure very low impedances in low frequency ranges, we need to be aware of this limitation and what we can do about it. Here's some images of how we would then hook up a common mode choke or a differential amplifier. Essentially, we have the output, device under test as usual, but then in series, we have a common mode choke, then hooked up to the input channel, or we do the same thing, but replace the common mode choke with a differential amplifier. There are pros and cons to both approaches, that is in the frequency range and the common mode rejection ratio, noise performance, and how easy it is to make these measurements. For our case, we'll be using the low frequency common mode choke. After having gone through the basics, calibration is next, and this is something we always have to do before we perform a measurement. This is to reduce or hopefully eliminate the effects of our measurement setup, that is the mounts, the fixtures, cables, connectors, anything that isn't the device under test we want to calibrate out. For this, we have two options. Either we have a through calibration, which is just a single calibration point, or an open short load or OSL calibration, which are 3 calibration points. The through calibration is easy because it's just one calibration setup, but the calibration point, because it's effectively an open, is that our impedance is measured at infinity, which is very far away from the impedance ranges we are actually measuring. Keep in mind, we're looking at maybe milliohms to hundreds or kiloohms. Whereas the open short load, we have 3 different calibration setups we have to do, but we're calibrating at 3 different points. At Z is infinity, Z is 0, and some known calibration resistance that might be 50 or 100 ohms. So typically you might want to prefer doing an open short load calibration. Again, the calibration must include the entire measurement setup. That's the cables, the common mode choke or the differential amplifier, connectors, DC blocks, and it's super critical for you to do this to achieve accurate measurements. Another thing is, how do you set up your calibration fixture? Your calibration fixture should emulate your device under test. That's the real measurement you'll be doing on your device under test. So if I'm measuring 0603 components, I'm not going to choose a short or an open that looks like a 1206 component. So you might want to choose your calibration fixtures to have the same physical dimensions and properties as your actual device under test. One other problem is, of course, there's not really a perfect open circuit, there's not a perfect short circuit, and there's not a perfect load. We'll have tolerances, contact resistances, and more, which, especially for low impedance and high frequency measurements, you might have to correct for. Once you've completed your calibration, it's always a good idea to measure known components or known system to verify your calibration is in order. For the Bode 100, you also have 2 calibration types. One is a full range, so that's the full frequency range of the instrument, but that does use interpolation, and this is something you should use if you're uncertain of what frequency ranges you actually want to look at and you just want to do a global sweep. If you have an idea of what frequency ranges you actually want to hone in on, you can do a user range calibration, which does not use interpolation. The calibration fixture and the text fixture we'll be using is a PCB I quickly designed. We have 4 sets of in-out B and C connectors, one for the open, one for the short, one for a load, which is a known 100 ohm resistor, 0603 package, and one for the device under test where I can solder on different 0603 packages such as capacitors, resistors, and inductors. This is a very, very specific calibration board for 0603 style packages. Of course, I could just use the last row here and solder on a 0 ohm resistor and a very high impedance resistor and leave the resistor unpopulated to do my calibration. But here I have 4 different positions to do open, short, load, and then finally the device under test. And all of these traces, all of these connections are identical between open, short, load, and device under test. So my calibration matches the physical parameters and properties of my measurement of the device under test. With all of this being said, we are now ready to perform the actual real-world calibration and then do some real-world measurements of some passive components. Let's begin by calibrating our measurement setup. What I've done is I've attached the Bode 100 output via a BNC cable to one port of my 2-port shunt tester PCB. The other side of that 2-port shunt tester PCB connector, a BNC cable, goes from that connector into the low frequency common mode choke. And from the output of the low frequency common mode choke, we go into the input, that is port 2 of the Bode 100, as we discussed previously. Now, what we have to keep in mind with the calibration and with the measurements is that this low frequency common mode choke has a somewhat limited frequency range or limited recommended frequency range. Looking at the webpage for this BLCM as well as the datasheet, we can see that the usable frequency range they say is DC to above 50 MHz, but recommended is 100 Hz to 10 MHz. And going into the actual datasheet, we can see insertion losses, return losses, and typical common mode rejection ratios versus frequency. So that's something to keep in mind, what you calibrate to, what frequency range you calibrate to. I'd suggest if you use this part following the recommended frequency range, that is 100 Hz to 10 MHz. However, if you're measuring something where you want to determine the parasitic or equivalent series inductances, you oftentimes will have to measure above 10 MHz specifically for multi-layer ceramic capacitors. So for us, we will just do a full range calibration from about 100 Hz up to 50 MHz. That is the maximum upper limit frequency of the Bode 100. But do keep this in mind, whatever you use, if it's a low frequency common mode choke or if it's differential amplifier, make sure you know its frequency limitations as well as its other limitations. For us, now let's go to the Bode Analyzer suite. I'll click on Impedance Analysis at the top and expand the Shunt-Through section. Again, we are shown the recommended impedance ranges, as well as what voltages we can not exceed at inputs and outputs. I'll select that measurement, and we're greeted with a typical measurement window. On the left-hand side, we can select start and stop frequencies. We'll change this to 50 megahertz. We can change the type of sweep, the number of points we actually sweep through, source levels, attenuators, receiver bandwidths. Depending on the resolution you might want to increase the number of points. The source level you want to adjust so you don't drive any nonlinearities into your measurement. That is, if you increase the source level too high, that might influence your measurements because you're exciting nonlinearities, you're overdriving, you're saturating, for instance, an inductor. So therefore, you want to adjust your source level that it is high enough to maximize the signal-to-noise ratio, but not high to excite nonlinearities. And you can adjust the source level and check between measurements. If the measurement changes, your source level is probably too high. The attenuators are for receiver 1 and receiver 2, and to see what they are, we can go to the impedance reflection setup at the top, and we can see this is actually how the Bode 100 is configured. So the attenuators are attached before the receivers 1 and receivers 2. Again, changing the attenuator will protect the receivers from overload, but also it can worsen your signal-to-noise ratio. So you want to choose them so you don't overload the receivers, or you want to choose the attenuators low enough to get maximum signal strength. 10 and 20 might be a good starting point, as Omicron Lab have put in here as a default, but I found that actually 10-10 works in this case quite well. So I'll change that attenuator 2 to 10 dB, and I'll change the source level to -6 dBm, and I'll leave the receiver bandwidth at 300 Hz. We could now straight away run a measurement, but we do want to calibrate. Again, we can do a full range calibration, which is the whole frequency range of the device, but this does mean the software will interpolate, whereas if we do a user range, this is without interpolation. For the sake of simplicity, we will do a full range calibration, so I'll click on full range, and now we can see we can either do a through calibration, as we saw, or a 3-point open short load calibration. And typically, open short load is preferred for the reasons we saw earlier, although it is more involved and it does take longer. If we expand the advanced settings, we can change some parameters. For instance, the load resistor. Actually, in our case, we're using a 100 ohm load resistor once we get to the load calibration, and we have a short delay time of 0 seconds as per default. So as I have this currently hooked up, I've hooked up the open calibration. Now keep in mind, this is without a 0 ohm 0603 resistor. You could put an 0603 resistor on the load pads of this calibrator and use that for the open short load calibration. It'd be interesting to measure the results and differences, but keep in mind you should set up your calibration and measurement test rig and jig for the actual measurement you'll be performing. So that's why I've defined my traces, my printed circuit board for these 0603 type measurements from the design we saw earlier. So with the open connection now in place, I can click on open and run this calibration. At the bottom of the screen, if you look at receiver 1 and receiver 2, you can see the receive signal strength. This is quite low, so we could probably either increase the source level or reduce the attenuators. But again, we don't want to increase the source level too much to saturate our components. Now we've done the open calibration, let's move over to the short. So having moved over the cables, the BNC cables, exactly the same measurement setup, except now I'm hooking up to this short interface, which is just a shorter ground right at the center, appropriately sized for 0603 type components. With that in place, click on short and that'll run through. Again, check out the receiver 1, receiver 2 signal strength. And for a short, that's of course going to be much lower because we're shunting essentially the energy pretty much directly to ground to the 50 ohms. Now let's move over to the load calibration. And the load calibration, I simply have a 100 ohm 0603 resistor with the same measurement setup and characteristics of the traces and the cables as before, connected with these BNC cables. With that in place, let's test the load. Remember to make sure your load resistor input here is what you have on your calibration setup. With the open short load calibration completed, we can click close and we can see we have this green box around the full range calibration, which means we now have a calibrated setup for this particular measurement. What we could do is go to the top left export and export the calibration data for this particular measurement setup, this particular calibration range for my particular environment I'm in my lab for this specific operating point. So you don't have to do this calibration over and over again for this same type of measurement. In any case, what we can do now is see that we on the right-hand side have default traces set up for 1 impedance magnitude and the trace 2 is set up for impedance phase. I still currently have my calibration test set up for the 100 ohm resistor, so I could do a single sweep from 100 Hz to 50 megahertz, and hopefully we should get straight lines for both the magnitude and the phase. They're both currently on the same graph, so I can go to View, Axis Placement, 1 axis per chart, and now right-click Auto Optimize to scale the graphs appropriately. Now what we can see here, we pretty much have 100 ohms all the way through, although we are reaching about 100.7 ohms at the higher frequency ranges, and the phase is also around 0 degrees, just to verify this 100 ohm calibration measurement. Now what we ideally want to do next is measure something that we know the characteristics of. This might be a 10 milliohm resistor, where at low frequencies we are measuring around 10 milliohms, plus minus some tolerance, and at high frequencies we know there's going to be some sort of ESL, equivalent series inductance component, that will kick in the megahertz range. It's important that you verify your calibration with a known measurement. We'll skip that for now and we'll move straight over to actually measuring a component. What we're going to do now is measure two different components, one inductor, one capacitor, and for this I will simply solder on either inductor, capacitor, or different device, different passive, onto these DUT pads which are 0603 sized, and I've moved my BNC connectors and cables over to the last row here. So with the calibration complete, back in the Bode Analyzer suite, I now popped on a 10 microhenry inductor, and I can click on single measurement to see what this impedance profile looks like. And this is pretty much what we can expect from a typical inductor. I've added a cursor in here at the top. If you follow this along, we can see the frequency, we can see the measurement for trace 1, which currently is impedance, and trace 2, which is the phase. So if I move all the way close to DC, we're starting from 100 Hertz, we can see this is where the DC resistance of this inductor tends to dominate. And we can see our DC resistance is measured at around 880 milliohms. Then our impedance profile is flat before the inductance kicks in, and this happens to be a corner frequency, let's say around 10 kilohertz, before we start in this upward sloping region of impedance, which is our inductive region. This is also where our phase now shifts to plus 90 degrees as we expect for an inductor. As we move further right in the curve, we increase in frequency, and we can see there seems to be some sort of self-resonance somewhere around 40-ish megahertz, where we have stray capacitance of our inductor causing that resonance before we drop down in impedance again. Remember, our impedance range is limited to 50 MHz due to the Bode 100, and also measurements after 10 MHz will be affected because that's outside of the recommended usable frequency range for our common mode choke. So do keep that in mind, that above 10 MHz we might have some inaccuracies in the measurement due to our common mode choke, and we can only measure up to 50 MHz with this instrument. What we can also do, if we go to the right hand side, we can change our measurement format. If we stay with impedance, we can change the format, for instance, to inductance. So I can change that to LS. Now the bottom curve shows inductance. And if we move along, looking at the trace, we can see this measures or calculates to be about 10 microhenries, which is exactly the inductor we're measuring at the moment. If we compare that to the actual part we're measuring, this is a TDK 10 microhenry and 0603 inductor, we can see it's 10 microhenry plus minus 20% tolerance, and they've measured this at 2 megahertz, and we're getting pretty much the same thing. And they have a typical DC resistance of 900 milliohms. And from our measurements at DC, we're getting pretty much 900 milliohms as well. What's also interesting, they show on their website an impedance versus frequency plot, and they also get this resonance at around 40 megahertz before the impedance drops off again. And that's exactly what we're seeing on our measurement as well. At around 40 plus megahertz, we're getting that impedance peak before we know it'll drop off afterwards. So that's already pretty cool. We can use manufactured data to verify our measurements, at least in part, and this again is an example of what we could use the shunt-through measurement for. I've now soldered on and replaced the inductor with a 10 microfarad 6.3 volts DC rated multi-layer ceramic capacitor from Murata with a 10% tolerance. So now let's see how this measures. Going back to the Bode Analyzer suite, clicking single, right-clicking and auto-optimize. This is what we can now see for our multi-layer ceramic capacitor. Again, 10 microfarads, 0603 package type. If you've watched the previous video on ceramic capacitor modeling, at low frequencies, we're getting our typical downward-facing capacitive slope. If we look at trace 2, which is set to capacitance, we can see we're getting about 9 microfarads, which is within the 10% tolerance of our 10 microfarad capacitor. If I change back my second trace to phase instead of capacitance, the phase is minus 90 degrees in this capacitive region, and then we hit the self-resonant frequency where the phase shoots through 0 degrees, and we get our impedance minimum. This seems to be happening at around 3 megahertz, and we can see we're measuring an impedance magnitude, very low ESR of 3.6 or 4 milliohms at that point. After the self-resonance point, where the equivalent series inductance and the capacitance cancel each other out and we're left with the ESR at that frequency, we then move into the ESL dominant region where the inductance dominates. We can change our measurement again from phase to inductance, and we can then get the cursor to measure around 150 picohenries of the ESL. Now, jumping over to the manufacturer tools, and Murata I quite like because they have this tool called Sim Surfing where you can explore all of these measurements that they've done on their end on their components. So I've typed in the part number, this is this 10 microfarad 6.3 volts rated X5R 0603 capacitor, and we can get the impedance versus frequency curve directly from them as well. And we can get the same characteristic impedance versus frequency curve, the low frequency capacitive region, our series resonant point, and the inductive region. And if we look at the lowest point at this resonant point, we can see the resonance frequency is 3 megahertz and the ESR at that point is 4 milliohms. Comparing that to ARM results, we also get a resonance frequency of 3 megahertz and an ESR of about 3.5 milliohms, which is a very good sign that our measurement is correct, that we can verify it with the manufacturer data. So I think this is pretty cool. We can use the Shunt-Through Impedance measurements setup to measure pretty low impedances in the milliohm range and with further care in the microohm range. And we can use this to measure component models, but then also in later videos, we'll see how we can use this 2-port shunt impedance measurement setup to measure actual PDN impedances of printed circuit boards. So I've got a test PCB here, which we'll see in a future video, but we can also use this measurement technique on real-world PCBs, probing out particular points to see what the impedance profile looks like, which I think is very, very exciting. Thank you very much for watching this video. I hope it was useful and I hope it gave you an insight into 2-port shunt-through impedance measurement techniques, what to watch out for, how to calibrate, and how to measure real-world components. If you haven't already, make sure to subscribe to stay up to date with any latest videos, especially looking at PDN impedance profile measurements, which I think is going to be really cool and interesting. If you have any questions, please leave a comment. If you like the video, please leave a like, and I hope to see you in the next video. Thanks again for watching. Bye-bye.